Double pipe already I discussed. Let's so I'll not cover too many things. Only double pipe. One pipe containing the tube fluid concentric with another pipe. So one pipe will be inside another pipe, and it should be concentric. Okay. So this is called double pipe. Okay, this is a double pipe heat exchanger. So tube is often finned to give extra surface area. So tube will be finned sometime. Fin, what is the purpose of fin? Fin means extended surface. Extended surface, like I have one surface and fluid is flowing over it. So what will happen? One laminar layer will be created, okay, near wall. So in laminar layer is created, heat transfer rate will be lower. So you create more turbulence, you create more surface area, because formula you can remember H A delta T. So if you can increase A area, your heat transfer rate will be increasing. So what you do? If this is a surface, so surface I will be creating fin. So fin will give me more surface area because this area extended. Initially surface area was like this, now this extra area added. Okay. So surface area increased, again you are creating loss of turbulence also, fluid will be creating turbulence. When your turbulence is created, fluid mixing will be occurring, cold and hot fluid will be mixing. When mixing up is happening, more heat transfer will be occurring. Okay. And another thing is that surface increased, again this is metal conductive surface. So this will be this fin area surface also will be heated with same temperature. Okay. So fin will be designed such a way that temperature will be almost same as main metal, and cold fluid or hot fluid, it will be touching the fins and surface, loss of turbulence, heat transfer rate will be increased. So in double pipe or any type of heat exchanger, you can use fin and you can increase heat transfer rate. So purpose of fin is to increase heat transfer rate using increasing area plus turbulence. Okay, turbulence increasing plus area, total area of the surface increasing, because H A del T. Okay. Hairpin or U-shaped single tube also can be used. So U-shaped, okay, this is hairpin type shape. So this type of also system also can be used. Okay, like this way you can draw whatever you like. One entry, one exit, one entry, one exit. Okay, hairpin shaped. It is cheap and readily available. Thermal expansion not problem for YouTube because you have extended portion, so expansion is not issue. Can be applied to most application in oil and gas area. Okay, when surface area 1000 feet square or less. Okay, we have direct fire heated and indirect. Okay, so in direct fire system, so you are giving direct heat to the fluid whatever you want to heat. Okay, so in that case radiation will be playing major role, mainly radiation through, like, so hot gas is coming, you are having one oven, right? You can remember this rural chula, right? So lots of fire will be coming, lots of, so direct radiation is heating actually, radiation and some convection. Conduction is not there because hot gas is going there. So hot gas is not touching any solid body. So only hot gas going and radiation going. That's why your pot or cooking pot will be heated up. Okay. So radiation mainly and convection will be playing role. Direct heating system. But indirect system actually radiation will be playing lower role. Okay. So rotary kiln, open hearth furnace, so that sort of application is there where direct heating is possible. So in that case radiation and convection basically. Indirect fire system, steam boiler, vaporizers, heat exchangers, melting pots. So all this will be using some other fluid, and basically convection and conduction maybe will be playing role. Fine. So okay, so we'll try to go to the problem directly. Okay, your time almost there. I have still 15-20 minutes. So if you are okay, let's try to go. Let's see. Okay, let's try to solve one problem based on whatever you learned in heat transfer and heat exchanger. So here one seawater cooler. Seawater means offshore application, cooling system. Total steam stream from, not steam, stream from the example field in its later stage of life of a flowing well, right, flowing well should be right. Temperature 175 degree to a field in its later stage of life, flowing temperature 175 degree Fahrenheit, to temperature 100 degree Fahrenheit to allow for the treating. Given data is given, gas flow rate, oil flow rate, water flow rate is given, and specific gravity gas, oil is given. Temperature, inlet temperature to the exchanger 175, pressure 1000 psi G. So, psi means you have to add 14.7. Okay. Water vapor in gas 16 pound mmSCF. Okay. How much water vapor is there? Outlet temperature 100 degree, pressure again psi G given, outlet pressure, water vapor in gas 28. Why 2 time given? Okay. So, exit, this is exit condition, this is inlet condition. Okay. So, 2 means exit condition. Limiting temperature rise 10 degree Fahrenheit. So, water temperature 10 degree will be rising, we are assuming, and tubing diameter 10 degree, again Birmingham wire gauge is given, tube of 1/4 inch pitch. So, distance between two tube is 1/4 inch. Tube length 40 feet, LMTD correction factor is given 0.95, area of tubing is given 0.2618, overall heat transfer coefficient also given, heat capacity also given, oil specific heat given, latent heat of water condensation given, shell made up of this one, copper and nickel, assume counter current heat exchanger. So, you can use co-current also. Just for simplicity I made one. So, in exam I can give co-current. Okay. So, the question is that water flow rate you have to calculate, heat duty you have to calculate, seawater circulation rate, number of tube you have to calculate. So, here a certain amount of gas and oil flowing, and oil is containing certain amount of water vapor. Okay. So, water will be condensing. So, how much total water is going out, how much total oil going out. So, that sort of, and how much heat will be required to reach this certain level. So, that you have to calculate, and number of tube also you have to calculate. Okay. So, here free water first. So, if you see this water flow rate 15 given, okay, per mmSCF. So, that means free water, that is free water actually. So, free water is 100 mmSCF into 15. So, 1500 BPD, WPD or BPD you can write. Okay. So, water flow rate outlet, water flow rate at outlet equals free water and water vapor condensate. So, you is changing temperature, so water vapor will be condensing. Okay. So, water vapor 1500 BPD and water vapor condensed, because temperature change 60 minus 28, 60 inlet, 28 outlet of water into 100 mmSCF. Okay. So, it will be 3200 pound per day, and you convert into BPD, it will be like this, 3200 divided by 150, it will be 9 BPD. Okay. So, water flow rate will be 1500 plus 9 equals 1509 BPD, or you can write BWPD. Okay. Barrel of water per day. Now, this question asks how much water will be flowing. Okay, free water. Now, heat duty. When we are calculating heat duty, how much heat required for gas, water vapor water vapor to liquid, then temperature change. Okay. So, gas heat duty for gas So, gas due to Cg, I have given you the problem Cg 31.3. So, Q Q Qg equals 41.7, this is formula, 100 minus 175, this is temperature, into 31.3, this specific heat, into 100 is giving this will be coming, minus will be coming 9789 000 BTU per hour. Okay, so gas heat duty. Now condensate heat duty. Condensate means how much heat will be required for condensate. Okay, so Q oil equals 14.6 Sg del T CO QO. CO value given 0.535, QO equals 14.6 into 0.77 into 0.77 into 100 minus 175. Okay, this is into 0.535 into 6000 given. So, it is coming minus 2707 0.000 BTU per hour. Okay, free water how much taking heat? Free water is taking heat, QW equals 14.6 into del T QW equals 14.7 14.6 into 100 minus 175 1509. So, this is given 1652 000 BTU per hour. Okay. So, water latent heat, because phase change occurring. So, water latent heat equals QTH equals W into lambda. So, they are using latent heat is lambda. So, if I put the values 3200 divided by 24 equals 133, okay, into 976.3. So, it is coming minus 133 00 BTU per hour. Okay, so total heat duty Q equals minus 9789000 plus minus 27070 minus 1652 minus 133. So, it is coming minus 14281 BTU per hour. Okay, this is heat duty. Now, water circulation rate. Okay. Okay, this problem bigger is given book actually. So, just I am giving here. Water circulation rate. Leaving? Okay. So, water circulation rate. So, water temperature rise 10 degree. Okay. So, Q water equals 14.6 T2 minus T1 QW. Okay. So, it is giving QW divided by 14.6 QW equals QW by 14.6 T2 minus T1. So, this is giving 14.3 cross 10 power 6 divided by 14.6 into 10 equals 97945 BWPD equals 2858 GPM. Okay, so this value is coming. So one more part is there. Heat exchanger, number of tubes. So LMTD you have to calculate. Okay, so LMTD, when you are calculating, first you draw this figure. So 175, 85, 100 and 75, T1, T2, T3, T4. So del T1 equals 175 minus 85 equals 90. Del T2 equals 100 minus 75 equals 25. So LMTD equals 50.7 degree Fahrenheit. So correction factor, if I use 0.95, then LMTD becomes 0.95 into 50.7, it will be 48.2 degree Fahrenheit. So number of tubes equals N equals Q by UA dash LMTD. I can see LMTD dash is better, L. So it is coming 14.3 10 power 6 90 into 0.2618 into 48.2 into 40. So it becomes 315. Here L is 40 actually and A is 0.2618. Now we will try to solve one gate problem. It came in 2020 petroleum engineering. In a one counterflow shell and tube heat exchanger, a liquid process steam Cp given is cooled from 430 degree K to 330 K using water having an inlet temperature 280. Process steam flows shell side 1 kg and tube side 2.5 kg. The overall heat transfer coefficient is U also given, U given 600. Okay. Cp water is given 4.2 and process gas, process liquid Cp is given 2.1. Then the process steam flows 1 kg per second and water flows 2.5 kg per second. Okay, overall heat transfer coefficient given. Now neglecting heat loss in the surrounding, required heat transfer area you have to calculate. So A you have to calculate actually. Okay, so in that case what you do, heat gain equals heat loss. So mH into Cp 430 minus 330. Okay, mCp delta mCp delta T heat transfer rate, right? So mCp delta T equals how much heat gained? So 2.5 into 4.2 T2 minus 280. Okay. So I should draw one figure actually. Counter current. So temperature 430 to 330 and another temperature is 280 and this one I don't know. Okay. So LMTD T2 having an inlet temperature 280 using water, the process steam flows this one. Okay. So this gives T value T1, T2, T3, T4. Okay, this gives T4 equals 300 K. Okay. So LMTD equals 430 minus 300 minus 330 minus 280 divided by logarithm of 430 minus 300 divided by 330 minus 280. Okay, so this is giving 83.33 K. So heat duty equals UALMTD. So 1 into 2.1 into 100 equals 600 into A into 83.33. Therefore, A equals 210 into 1000 divided by 600 into 83.33. So, it is given 4.2 meters square. Okay, this is the solution. So, another problem, similar counter current heat exchanger, the hot fluid enters. Okay, so hot fluid enters 175 degree Fahrenheit and exits 100 degree Fahrenheit and exits 100. The cold fluid enters 75 and exits 85. Uh, 85 degree. For the calculation of heat transfer rate, consider the tube surface area to be A is given 0.26 feet square per feet and tube length 40. Overall heat transfer coefficient also given 100. The minimum number of tubes required, a heat duty Q is given 15 into 10 power 6. Okay, therefore N equals Q UA LMTD. Okay, and LMTD del T1 equals 175 minus 85 equals del T2 equals 100 minus 75. So, LMTD equals 175 minus 85 minus 100 minus 75 divided by logarithm of 175 minus 85 100 minus 75. So, it is giving 50.78. So, so N value is coming like 1.5 into 10 power 6, U value 100 given, A value given 0.26, LMTD given 50.78, L value given 40. So, number of tube will be minimum number of tube. Like again another problem, cell and tube heat exchanger use cooling crude oil from 400 to 360 degree. Crude oil flows through 3650 kg per hour. Water enters shell side 310 per Kelvin and has flow rate 1600. Assume heat capacity crude oil and water 2.5 and 4.187 with the overall heat transfer coefficient U again given, counter current heat exchanger given. So, heat transfer area, what is the heat transfer area? So, again U equals 300, QO equals 3650. First you draw this curve actually, this counter current heat exchanger 400 TW2 60310. Okay. QW given 1600, CO given 2.5, CW given 4.187. So, LMTD equals 400 minus TW2 minus 50 divided by ln 400 minus TW2 50 equals 350 minus TW2 400 minus TW2 divided by 500. Okay, TWT means exit temperature of cold fluid. So, heat released by oil HO equals 3650 into 2.5 400 minus 360 equals 3650 into 2.5 into 40. The water absorbs HW equals 1600 into 4.187 TW2 minus 310. Okay. Now, HW equals HO. This implies 3650 into 2.5 into 40 equals 1600 into 4.187 T 4.187 TW2 minus 310. Okay. So, TW2 minus 310 is coming 54.487. So, TW2 equals 364.484 K. Therefore, LMTD equals minus 4.484 divided by 0.7103 equals 42.35. So, it is coming. Okay, now UA LMTD equals HO. So, therefore, 300 A into 42.35 equals 3600 into 2.5 into 40. So, this will be giving A equals 7.98. Okay, this is the answer. Thank you very much for watching the video, and you have to prepare all the problem, and you have to see textbook or get questions similar questions, and you have to try to solve for preparing for exams. Thank you very much.